All right, so let's start by going over the quiz. Everybody hear me fine? I got my volume on right? Let me know. And essentially everything that we do today is going to be a review for the exam on Monday. So think of this as all stuff that is good to know for the exam, and I will expand on some of the things from the quiz. So the first question on the quiz, we're after functions whose graph has these x-intercepts, 3, -4, and -5. So it's supposed to mean, that means it has factors x minus 3, x plus 4, and x plus 5. And there's only one option that has those factors, B. It doesn't matter what order they're in. And the number in front doesn't matter. It doesn't matter whether you have a 2 or -3 or 4 or -7. That doesn't affect where the x-intercepts are. It does affect the y-intercept. And so an example similar to this that would be more difficult that could show up on the exam next Monday is maybe I'd tell you the y-intercept as well. And maybe it'd be a problem where you have to show your work. And you would have some arbitrary constant, call it A, in front of this. I'm going to go ahead and do it with the particular answer here. And you'd have to figure out what value of A gives you whatever y-intercept that I tell you is the y-intercept. So for example, if I say the y-intercept is 2, that would mean f of 0 would have to be 2, and you would have to solve for A by plugging in x equals 0 and solving for A. This would be a -60 here. Looks like A would be 2 divided by -60. -1/30 would satisfy this condition here. It's not the condition in this problem, but it's an example of how I could generalize this problem and something you should be able to do. Number 2, which one's the true statement when B is positive and not 1, little b? I actually should have said a little bit more here. This is not stated in the best way. I should have also said capital A and capital B are positive as well. But that would be understood that one of these has to be right, so that must be the implicit assumption. And the correct one is that the log of a product is the sum of the logs. That's C. The log of the product, A times B, is the sum of the two logs. Now, if that's not something that you remembered, you can figure it out by trying to consider examples. So for example, if you were thinking about log base 10 of 1,000, for example, well, 1,000 is 10 times 100. Log base 10 of 1,000 is what? It's 3, because 10 to the third power is 1,000. And then you'd wonder, okay, does that equal log of 10 plus log of 100? Yes, it does, because that's 2 and that's 3. Oh, that's 1 and that's 2. Would be an example of something that you can do if you don't remember which rule is true to help you figure it out. It's not a proof, but it helps you remember. A proof of this could be on the exam. We went over one in class. I also went over one in the lecture, one pretty similar to this actually in the lecture. Don't just assume you're going to be able to figure it out when you come to the exam without studying. Okay? You need to look back and think about it. You need to practice it. Number 3, what is the amplitude of the sinusoidal function? Excuse me. When it's in this form, some number times sine of something or cosine of something plus some other number, the amplitude's always that number right there. 2. What does that mean? What does it represent graphically? It's half the distance between the peaks and the valleys, the maxes and the mins, half the vertical distance. So this one has a vertical shift of 5, so it's centered at y equals 5. Having an amplitude of 2 means the highest value is 7 and the lowest value is 3. By having the +4 in there, it makes it more complicated as far as trying to graph it. I will talk about that in a second here, but just realize that the highest value is 7, the lowest value is 3. The amplitude is half the distance between the max and the min. 2. It's the number right there. What's the period? In part D. The period is always 2 pi divided by whatever number's in front of the x or in front of the t. In this case, it's 2 pi over 3. Dividing by a fraction is the same as multiplying by its reciprocal, so the 2 pi's cancel and you're left with 3. The period is 3. You also can make sense out of that by saying, well, what do I need to put in place of x here so that this thing increases by 2 pi units? Because the basic cosine or sine has a period of 2 pi. As x increases, say, from 0 to something, when does this thing increase by 2 pi units? When the multiplier here, this x value is 3, so that the 3's cancel, giving you a 2 pi there. We'll come back to graphing it here in a second. This one, what's the horizontal asymptote? It is a rational function where the degree of the bottom and the top are the same. Here I gave it to you in factored form. On the exam, it might not be in factored form. You might have to factor it. Either way you think about it, whether it's in factored form or if you expand these out, the ratio of the x squared term would be 1 on the top and 2 on the bottom. And the degrees are the same. Therefore, it does have a horizontal asymptote at that ratio, 1/2. 1/2 is the answer. If I added an extra factor down here, like an x minus 3 or something, or x plus 3, I don't want to cancel the x minus 3s, to make the bottom have a higher degree than the top, then in spite of the fact that the coefficients of the highest powers are still 1 and 2, the answer would be y equals 0. And if I made the degree of the top bigger than the degree of the bottom, no matter what those coefficients are, the answer would be it has no horizontal asymptote. So these are just factual things you should know. I mean, you can check them with your calculator. That's fine, though it is time consuming sometimes. And you don't want those kinds of things to slow you down. The exam is timed. You will feel some time pressure. The note card is just there for your security. You really should practice enough that you don't need a note card. I'm serious. I'm super serious. Practice those old exams, maybe even time yourself. Give yourself, what do we have for our class? We have an hour and 10 minutes for our class, 70 minutes. Time yourself for the old exams. Start to feel that time pressure. As far as checking your answer, well, one of them I think I give some answers for, but for the other I haven't had time. You could check with a friend and compare your answers. But you need to understand that knowing stuff is good for doing well in exams. And it's also good for problem solving, because when you know stuff, when it's in your head, well, you may not remember it exactly, but you kind of remember it. It helps you look stuff up. It helps you think about it quicker. It's worth the time investment to practice stuff and feel confident that you could do fine even without a note card. And the note card is just there for your security. 3x5, front and back, whatever you want on it, but it's just there really mostly for your security. The people who spend too much time on their note card, too much time experimenting with their calculator, usually run out of time on the exam. The plus or minus 1 are not asymptotes. I did make those match the vertical asymptotes, but that's at x's plus or minus 1, vertical lines or vertical asymptotes. So this is kind of a nonsense answer there. Let's come back and graph this function, this 2 sine 2 pi x plus 4 in the parentheses and then plus 5 outside the parentheses. I mean, yes, certainly you can use your calculator to graph it, but let's try to think about graphing it without a calculator. And yes, we have the amplitude, we have the vertical shift at 5, we've got the period of 3. That's all helpful. But because of that extra +4 in there, it makes it a little extra tricky. And what you want to do is you want to think of that as a horizontal shift, either to the left or the right, by imagining factoring out a 2 pi over 3 from 4. And you scratch your head and say, how in the world can I factor a 2 pi over 3 out of a 4? Well, you can. 4 can be thought of as 2 pi over 3 times something. What is the something? Well, the 2 pi would have to cancel. So having a 2 pi down there would be a good idea. The 3 is going to have to cancel. So having a 3 up there would be a good idea. And you want to be left with a 4. There's what you need to multiply it by to get 4. The 2 pi is canceled, the 3 is canceled, leaving you with a 4. In other words, this expression right there, 12 over 2 pi, which reduces to 6 over pi, is the number that would go right here if I factor out a 2 pi over 3. 6 over pi. What is 6 over pi approximately? I don't know. Something slightly less than 2. 6 divided by pi. About 1.90986, say. Approximately 1.90986. About 1.9. It's a little tricky. There's an x plus that in here. Does that represent a horizontal shift to the right or to the left? It's tricky.
Is it to the left?
You're correct. It is to the left. It's tricky. You would think with a plus sign there, you go to the right. But no, when it's a horizontal shift, you go to the left when it's a plus sign. Why? Here's an intuitive way to think about it. What would you need to replace x with to make this equal to 0? You'd need to replace x with negative 6 over pi, negative 1.90986. In other words, when x is negative 1.9 approximately, the sine function is at its value when the input is 0. Because when x is about negative 1.9, the input is 0. The sine function starts at its midline, its average value at the input of 0. So yeah, back here at about negative 1.9 in this graph, that's when you're going to go on your upward swing. The period is 3, right there. So we have to go up, then down, then back up again within 3 units of time. And if this is about negative 1.9, 3 units of time would then be negative 1.9 plus 3 would be about positive 1.1, approximately. We got to go up and back down, then back up again within that amount of time. It's going to look something about like this. Like that. And then it's periodic. It keeps going like that forever. It's going to go back up to where it started within about another 3 units. The period is 3. Period is exactly 3. But these numbers, negative 1.9, positive 1.1, and positive 4.1 are approximate because I was approximating 6 over pi to be about 1.9. That's not something that you can remember really easily without practicing for most people. Practice that kind of problem. I thought about also asking you a problem on this quiz where you had to solve a trig equation. That's something you should be able to do for the exam on Monday. For example, figure out where does this function equal 6, for example? What x value will give you an output of 6? Well, there's actually infinitely many answers because that horizontal line there crosses the red graph infinitely many times. We're just after one answer. If you're after one answer, it's good enough to use an inverse trig function, in this case, an inverse sine function. Set 2 times sine of 2 pi over 3x plus 4, I'm writing it in the unfactored form here, plus 5, set this equal to 6 and solve for x. It's a trig equation. You can't isolate x without applying the inverse sine function. You can isolate the sine of this first, subtract 5 from both sides, and then divide both sides by 2. Also, I'll do 2 steps in 1 here. Sine of 2 pi over 3x plus 4 would be 1/2 then. I did 2 steps there. I subtracted 5 from both sides, and then I divided both sides by 2 after that. Now you can apply the inverse sine function. But the inverse sine applied to this side cancels the sine, so to speak. Or does it? Well, you are, in reality, when you do this, restricting the domain of the sine function to a place where it's 1-to-1 and passes the horizontal line test. Because of this, just realize that the inverse sine function is just going to give you one possible answer out of infinitely many. They undo each other here. You're left with 2 pi over 3 times x plus 4 equals inverse sine of 1/2, which you also are allowed to write as arcsine of 1/2. Those are the same thing. But that is not sine of 1/2 to the -1 power. It's not a power there. If you meant sine to the -1 power, you'd actually write it as either 1 over that sine, or you'd write cosecant. 1 divided by the sine function is the cosecant function. But you don't have a cosecant button or inverse cosecant button on your calculator. Most people don't, at least. Not quite done. We need to solve for x now. Subtract 4, and then divide both sides by 2 pi over 3, which means multiply both sides by 3 over 2 pi. And then in the end, what that gives you is one possible answer. X will be 3 over 2 pi times, in parentheses, inverse sine of 1/2 minus 4. Now, actually, the inverse sine of 1/2 is a special number that theoretically you should have memorized, but you probably don't. Perhaps, or maybe if you want to impress me, maybe you do. Most people don't have it memorized, but this is a special number involving pi. Does anybody happen to know what it is? Inverse sine of 1/2. It involves pi.
Pi over 3.
That was a guess. That would be inverse cosine of 1/2. Pi over 6. This is pi over 6. And if you're not sure, you can always use your calculator. Inverse sine of 1/2 is that is the same as pi divided by 6. Okay, subtract 4, and then multiply by 3, and then divide by 2 pi. Making sure to use parentheses like I'm doing here. We get approximately -1.66 for this answer. Which answer is it giving it to us on this picture? It looks like it's giving us, looks like it's giving us this answer here, actually. Right there. -1.66. How could we get other answers if I asked you for other answers? Well, you could, since the period is 3, you could add multiples of 3 to this. This number plus 3 would give you this number. Add another 3, you get this number. Use the period. You could also, figure out how far this number is from -1.99 and subtract that from this number that's about, excuse me. Okay, it's a little trickier than that. Yeah, I probably better not do it. tricky, but certainly adding multiples of 3 works. That's harder problems, but it's stuff you should be able to do for exam 1. All these things are things you should be able to do for exam 1. I also thought about asking you about some factual questions related to dominance, but we haven't done a ton of examples like that in class. It was in the reading. I think we did one example. I emphasized, for example, that when you've got a power function, as far as which function dominates as x goes to infinity, it's the one with the higher power. So, for example, even if the coefficient in front of the power of x is small, like 0.00001, if the power is high, that's going to dominate another function that might have a big number in front, but a small power of x, and I'm being extreme here on both ends. And I'm not really worrying about how many zeros I put, I just arbitrary number of zeros. Dominates as x goes to infinity. And in fact, you can think of it as another extreme. I could even replace this power here by a pretty large power, maybe just one number less than that. I could even replace this by a 9,999. But because that power is 10,000, one bigger, in spite of the really small number there, this would still dominate that. The power is what matters. How big is the power? So I don't even have to go extreme with a very small power. I could make it a big power, just make it less than that. And this would still be true, is what I'm saying. It's also the case that any power function, no matter how small the coefficient is, and no matter how small the power is, dominates any logarithmic function. Even if you got a huge number in front of it. And by the way, if you tried comparing these things with your graph, the answer would seem to be the opposite. So this is just factual knowledge to know. If you graph both of these functions, it would look like that one is going bigger faster because that coefficient is so much bigger and that power is so small. But eventually, the point is, I claim, eventually this one would catch up and pass that one. It would grow faster, higher once x is big enough. How big would x need to be? Probably very, very big. I don't know, in the millions or billions or trillions, or maybe, I don't know, even 10 to the 100 power for all I know. I'm not bothering to try to figure it out. And you should know that exponential functions dominate any power function. So I could go 0.0000001 times 1.0000001 to the x. That's going to dominate any power function, even if I have a really big number here and a really big power here. Yeah, and you'll be deceived looking at your calculator. That'll grow seemingly much faster than that one, but guess what? In the long run, the exponential function where the variables in the exponent wins out. Now, rarely in real life applications do you have to think about such extreme examples. The point is you should know the facts. So I thought about asking you quiz questions, but I didn't, but those could be on the exam. The beginning of chapter 2 could be on the exam as well. Derivatives, slopes of secant and tangent lines, and then the application to motion, position and speed, and also, well, distance traveled and speed, and then position and velocity, and thinking about those graphically as we've been talking about this week. And then limit calculations, and understanding the idea of what it really means for a limit to be true. We did one example in class on Wednesday. Let's do another example. Before we do the example related to what we did in class on Wednesday, let's address the issue of that example we did where when we used Mathematica, at least it was deceiving. Remember this example? Find the limit as x goes to 0 of square root of x squared plus 9 minus 3 over x squared. I think we did this either a week ago or on Monday. Mathematica had trouble showing you what happens as x is really close to 0 here. Let's try it on a calculator and see if the calculator has similar trouble or not. So I'll plug in this function, square root, oops, I need parentheses here. Square root of x squared, oops. Plus 9 onto the square root, then put a minus 3, all divided by x squared pick a window near 0. We'll try initially -5 to 5 in both directions. It's pretty close to 0. I guess I better zoom in the y direction. Let's just go from 0 to 1. It's not a horizontal line. It does change. Let's zoom in a bit closer in the y direction. It looks, for all we can tell, like this function has a limit as x approaches 0. Some limit, this is 0, 1, 0.1 and 0.2, some limit between 0.1 and 0.2. You could try tracing to estimate it if you like. Trace. Oops. When x is close to 0 but not equal to 0, y is close to 0.16 repeating perhaps. 1/6. Does that get confirmed if we zoom in closer? Let's change the window here. Let's let x go from -0.01 to positive 0.01. And let y go from 0.15 to 0.18. See what it looks like. Looks horizontal. It's not horizontal. Just looks that way. Yeah, it's looking normal here still. Let's zoom in further. Let's see if the calculator has trouble like Mathematica did. Let's try 5 zeros and a 1. Just interested in what happens here with the calculator. Okay, it's not giving me anything. Interesting. It's like just not even graphing it at all. I don't know why. I thought it would try. Okay, let's fix this a bit. Negative. Try 3 zeros and a 1. Oh yeah, there's something a little weird going on. Let's add one more 0. Yikes. Yeah, the calculator is having trouble too. Is that really what's going on? No, that's numerical error. When computers deal with really small numbers, like we have in both the numerator and denominator as x is close to 0. Both the top and the bottom get close to 0. Right? When x is close to 0, x squared is certainly close to 0. When x is close to 0 on the top, this is close to square root of 9, which is close to 3. Minus 3 is close to 0. Both the top and the bottom are getting close to 0. When that happens with technology, because of the fact that the technology can only represent things in a finite way, errors accumulate. So this is an example of something you can't trust your calculator on. Can it be done? Can you figure out the limit some other way? It turns out you can, and I'm going to go ahead and show you. Should you be able to do this kind of thing on an exam? Maybe if I gave you help. And the help I would give you is I would give you the hint of multiplying by 1 in a special way. And here's the special way. Square root of x squared plus 9 plus 3 on both the top and the bottom is the special way to multiply this entire fraction by 1 in a way that will help us solve the problem. That's not obvious, but that's going to work. This was a trick that people had to figure out. Carry the limit sign along, expand out the top. You got a FOIL because it's the product of two binomials. First times first is the square root of x squared plus 9 times the square root of x squared plus 9. That's x squared plus 9. The square root goes away, right? Come on, get rid of this jump call here. No. Outside times outside, I'm not going to write down. It's 3 times that square root. Inside times inside is negative 3 times the square root. Those cancel. I'm not going to bother writing them down. And last times last is negative 3 times 3 is negative 9. Hey, wasn't that cool? That makes the top a lot simpler. That's why I did what I just did. Because it makes the top simpler. Now, it makes the bottom more complicated. So you're like, did we really gain anything? But amazingly, we did gain something. When we cancel the 9s, then we realize we can also divide out the x squareds, which is okay to do because remember, with a limit, it doesn't really matter what happens to the function at x equals 0. I can divide out the x squareds there and be left with a 1 on top. And then what I'm left with is continuous at x equals 0. All these things I'm saying are things you should be able to write down for reasons. Cancel it. Dividing out there is justified because of the definition of a limit, not depending on what happens to the function at 0. Allows us to say if these limits exist, they are the same thing. And then this function here is continuous at x equals 0. When I plug in 0, I do not divide by 0. It's continuous there. Therefore, by continuity, I can plug in 0 to get the final answer. 1 over 3 plus 3, which is 1/6. Sorry. Hey, yeah, 1/6. 0.16 repeating. Shouldn't this go away? There we go. We can do better than technology here. That's good. The technology is not our overload yet, but maybe the day is coming soon. Hopefully not.
Is it supposed to be a positive 3 when you're multiplying out?
Yeah, the +3 there is what allows the outside and inside products to cancel, because you got a +3 square root there and a -3 square root there. And so when I FOIL, I did use FOIL in my mind here. The outside and inside products cancel, and that's why it's nice to do this with the +3 in the top and the bottom. Is that your question?
Yeah.
I would, if I gave you a problem like this, I'd give you this hint. But you should be able to take it from there. If you graph the original function here, or this function for that matter, which are the same thing, the graph does have a hole at x equals 0. But when you divide that out, you've now made a continuous function at x equals 0. So it's kind of the opposite of what you were saying. It actually gets rid of the hole. And I am dividing it out. I'm not left with a 0 top. I'm left with a 1. Because x squared divided by x squared is 1 when x is not 0. The value at 0 doesn't matter here. It does here. We can plug in 0 because that's a continuous function at x equals 0. Let's go back to the limit example of the type that we talked about at the end of class on Wednesday now. Let's do a different example. The limit as x approaches, let's say, 4 of x cubed is, well, it's 4 cubed, which is 64. That would be justified by saying, well, x cubed is continuous everywhere. That's a justification for that calculation, since x cubed is continuous everywhere. When you can evaluate a limit by plugging the number in, that's a consequence of the continuity of the function. But say we were thinking about how close does x need to be to 4 to make x cubed within 0.1 units of 64. How would you answer that question? Answer with technology. How close should x be to 4 to make y equals x cubed within epsilon equals 0.1 units of 64? The fact that the limit is 64 means that I should be able to find a values of x close enough to 4 to guarantee this works. And that's no matter how small the epsilon is. I picked 0.1, I could have picked 0.00001, I could have picked 10 to the negative million power. No matter how small epsilon is, I'm guaranteed of success here because the limit truly is 64. If you were wrong in what you thought the limit is, if you thought the limit was 63.999, a wrong answer, you would not be successful if I made epsilon small enough. Let's think about, we thought about it symbolically in class on Wednesday. We will think about it symbolically here as well, but I'm not going to write as many words. I'm just going to think about a picture here. Pretend this is a calculator window. In the vertical direction centered on 64 and the horizontal direction centered on 4. The epsilon is going to represent a vertical distance from 64. And this number, therefore, is going to be 64.1, and this number down here is going to be 63.9. I want to figure out what my x min and x max should be to make sure the graph stays in the window the entire time, and maybe looks something like this. It does go through the point 464. I want to find a number, it's traditionally called delta, lowercase delta, so that when x is between 4 minus delta and 4 plus delta, the output f of x, or y in this case, is between 63.9 and 64.1, just like I'm drawing it. I would not be successful if the graph looks like what I'm about to show you here, but not actually draw. If the graph looked like this, see what my pen's doing there? In other words, if it's exiting the top and the bottom, that means I was not successful because there'd be x values in this range here whose outputs would not be between 63.9 and 64.1 in that case. Actually, let's just do it experimentally. I mean, I could do it with some algebra. I I could set x cubed equal to 63.9 and 64.1 and solve for x like I did with the x squared problem on Wednesday. But let's just do it purely with calculator experimentation here this time. So simpler function, it's just x cubed. I want my window to be centered on 4 in the x direction and say symmetric. Let's just initially try 3.9 to 4.1 and make the scale like 0.01 or something. And the y direction, I want it to be centered at 64. And in fact, I want, since epsilon is 0.1, I want it to be from 63.9 to 64.1. Now, in my mind, I know something. I know that the derivative of this function at 4 is fairly large. In fact, doing it in my head, should be 48. It's a pretty steep graph on an ordinary kind of scale near this point. This picture is not a very ordinary kind of scale if we want to make it look like that. So what that means is I'm guessing that the delta actually needs to be much smaller than the epsilon. And here in picking 3.9 and 4.1, I picked delta to be 0.1. It's not much smaller. It's in fact equal to epsilon. And that's going to mean the graph's going to look pretty steep in this window. I'll graph it. It's going to be pretty steep. It's going to go out through the top and the bottom. Yep. I was not successful. Okay. Fix it. Try a smaller delta, like 0.01. Try going from 3.99 to 4.01. Am I successful now? I'm certainly going to be closer to success, but it's not obvious that I will definitely be successful. It's less steep, but still steep enough to go exit the window through the top and the bottom. All right, let's try 0.001 for delta. There, now I have success. Is that the smallest delta that works? No, probably I can get away with something bigger, like maybe 0.002. But certainly delta equals 0.001 works. So 4 minus delta is 3.999, and 4 plus delta is 4.001. That works. Probably 0.002 works as well. Maybe even 0.003. I'm not sure. I'd have to try it. What we're trying to get across here is just the basic idea of what it means for the limit here to be truly 64. It means I can get arbitrarily close to 64 within epsilon for the y values. I made epsilon 0.1. I could have made it smaller by taking x sufficiently close to 4. Delta is the measure of sufficiently close. Just trying to get a basic idea of what that's about with an example. It should not be surprising if you find it difficult. It is a difficult concept. In fact, Newton and Leibniz didn't even know this concept, even though they invented calculus. They didn't have a completely rigorous understanding of limits. That didn't come along until like 150 years after they died, or maybe, well, maybe 100 years. Into the 1800s until people figured out what limits really mean. And they were motivated to do so because there were some weird things that could happen that I would like to address at some point in the semester. Something related to Fourier series, if you've ever heard of that. In Fourier series, weird things happen, but it is a very important subject. In fact, it's key to how our society works, the modern world, with our technology. Our technology, whether it be TV, radio, phones, whatever, would not be possible without Fourier series and its extensions. Image processing is another example. So there were reasons why they said, okay, we need to really understand limits better than we do. All right, we got 8 more minutes. Everything we've done today is review. But we haven't highlighted everything you should know. Okay, so let me just verbally highlight some things you should know. I think I probably won't take the time to write it down. So you gonna want to listen and write to some degree yourself. I do put these things, I put these things on YouTube. You can watch these, the last 7 minutes here is what we got. So section 1.1, I guess we can look at the book at least, was about just functions in general. Functions and change, including linear functions whose graphs are straight lines, like this one here. Including knowing slope and intercept and being able to find equations of lines and interpreting slopes as rates of change. Domain and range, being able to understand that graphically and symbolically. Those are all things highlighted in section 1.1. Families of linear functions down here, slope there. Proportionality is highlighted as well, increasing and decreasing. Those are definitions in section 1.1, but your problems were not limited to those kinds of functions. They involved nonlinear functions and thinking about domains, trying to avoid dividing by 0 or taking square roots of negative numbers, for example. Also emphasizes the theme of the rule of 4, we call it, that you can think about functions either symbolically with formulas, graphically with graphs, numerically with data, like a table of values, or verbally, because that's important for problem solving. Like these problems are verbal. Well, these problems are good examples of verbal problems combined with graphical. We thought about this particular one in class, I think. I'm not sure. Okay, so you want to be comfortable with that. Be able to read a graph, so to speak, understand what it's telling you. The next section was about exponential functions. You should be able to convert between the arbitrary base form, the book calls it A, I think I called it B in class, and base E, where E is the special number, about 2.71828. We're going to see why E is so special here very soon. You should be able to convert back and forth between these using logarithms, the natural logarithm, which comes in section 1.4. You should be able to solve exponential equations for the unknown exponents using logarithms. Knowing what their graphs look like, knowing that you get a constant percent rate of change with exponential growth or decay, not a constant slope, constant percent rate of change. And for example, we emphasized that if you've got something like this, 4 times 1.06 to the t power, that represents 6% growth per unit time. The 0.06 can be interpreted as a 6% rate of growth per unit time, a relative rate of growth. Concavity was emphasized, concave up and concave down, you should be able to identify. And dealing with data, again, numerical, identifying whether something seems linear or exponential. I emphasize that in the lectures a little bit more depth than I did in here. It's something if you feel like you're weak on, you might want to watch part of the lecture on that. New functions from old included being able to deal with horizontal shifts, vertical shifts, horizontal and vertical stretches and compressions, translations, yeah, vertical shifts, inverse functions, composite functions, all that stuff was in here. Being able to solve for inverse functions, we talked about that a lot. 1.4 is on logarithms. 1.5 on trig, you should be able to do the kinds of problems we've emphasized there, using logarithms to solve exponential equations, using trig functions to represent periodic functions like we've been talked about for the quiz, and solving with inverse trig functions. Knowing your facts about powers, polynomials, and rational functions. Haven't had time to do that application that I talked about. I wanted to do today, but we didn't have time. So that will not be on the test. I hinted at an application involving bond prices. Probably next Wednesday after the exam, we'll talk about that. Continuity limits, basics of derivatives as well. So you've got the old exams, two old exams, one from a year and a half ago and another one from further back. And I think the one from further back's got some answers. I don't know that I'll have the time to write answers for the one from a year and a half ago, because I got other things I need to get done as a higher priority. But you certainly can check answers with each other. You can check answers with Math Lab. Sunday night would be good. Not everybody can go in person, so you may need to sign up virtually if you want to go. And like I said at the beginning of class, take this seriously. Study well enough that you feel confident that you could do well even without a note card. And then make your note card at the end. It's there mostly for your security. Try to do the exam without looking at it, because it can slow you down too much. Think of this as your best chance for the rest of your life to feel like you've got your functions and precalculus knowledge down solid, plus a bit more with limits and continuity and derivatives. Okay? Use whatever resources you need to. We'll see you on Monday. Those who want to take it, need to take a distance, you need to tell me ahead of time.